Hello, everyone, and welcome to today's lecture. Today, we're going to be talking about graph traversal. But before that, let me review what we covered last time. So last time, we spoke about sparse matrix computations. It was part two because the lecture before that, we had spoken about sparse matrix computations as well. And we looked at three different formats, which were COO, CSR, and CSC. And we left off by observing that when comparing CSR and COO, CSR had the advantage that it avoided atomics, but it had the disadvantage compared to COO that the memory accesses to the matrix were not coalesced, and it had some control divergence. So we asked ourselves the question, can we design a format that avoided atomic operations, but at the same time achieved coalesced memory accesses and avoided control divergence? And that led us to look at two other formats, which were the ELL and the JDS format. So in the ELL format, we logically grouped the non-zeros by row, like we did in CSR. However, what we did is instead of flattening it horizontally, we added these padding elements so that each row had a fixed width after you consider the padding. And then we stored the non-zeros by column instead of by row. And that way, sorry, not by column index, but by the column in this compressed array. And that way, if we look at the flattened version of this matrix, when every thread goes to access the first non-zero in its row, these accesses are coalesced. And then when they go to access the next non-zero in the row, the accesses are coalesced, etc. And because we're assigning a thread to each row, there are no atomic operations because each thread is only going to update one output element, and that output element is only going to be updated by one of the threads. So we saw how ELL avoids atomics and at the same time gives us coalesced accesses to the input matrix, but we still had the control divergence issue. One way to solve the control divergence issue, the control divergence is by having a hybrid ELL and COO format. So here in this matrix over here, we have these two rows that are very large, and this has two problems. The first problem is that it creates a lot of non-zero padding elements that waste space, and also it creates control divergence for the threads that are in the same warp as the thread processing the very long row. So to avoid this, what we did is we had a hybrid ELL and COO format, where for the very long rows, we truncated them and we placed their non-zeros in a COO representation, and we only represented kind of part of those rows in the ELL format. And by doing this, we kind of mitigate how much padding we have. We also guarantee to have better load balance for the ELL part when processing the ELL part of the representation, while leaving the excess non-zeros for the COO. And we know that COO SPNV also has good coalescing and good load balance. But then there was another way of having better control divergence, and that is when we group the non-zeros, instead of just adding padding elements, we instead sort the rows by their size. And then when we sort the rows by their size, now when adjacent threads are assigned to adjacent rows after sorting, they will be assigned to rows that are similar in length, and this will reduce the amount of control divergence. And then also to ensure that we have memory coalescing, we want threads, when every thread accesses their first non-zero, we want them to access adjacent elements in memory. So what we do is we store these elements according in a column order instead of a row order, or in otherwise, we put all the first non-zero of all the rows together, then the second non-zeros of all the rows together, then the third non-zeros of all the rows together, etc. So if we flatten this is the JDS format. We have this iteration pointer that tells us where the non-zeros of each iteration begin. So here it tells us where the first non-zero of all the iterations of all the rows are. Here it tells us where the second non-zero of all the rows begin. Here it tells us where the third non-zeros of all the rows begin. And that way, when the threads access the non-zeros, their accesses are coalesced, and also we've mitigated the control divergence because adjacent threads will iterate over similar row lengths. Okay, this is what we covered last time. Any questions before we move on to today? Is everything clear? Okay, so then today we're going to be talking about graph traversal. So before we talk about how to process graphs, let's talk about how to represent graphs. So first of all, what is a graph? A graph is basically a data structure where you have a bunch of vertices, and these vertices are connected by edges, right? So here I have a vertex 0, vertex 1, vertex 2, vertex 3. Here I have an edge from vertex 0 to vertex 2. This indicates that there's some connection going from 0 to 2, this vertex, etc. And one typical way of representing graphs is using adjacency matrices, right? So here we can have every row represents the source vertex, and every column represents the destination vertex. And wherever I have an edge between two vertices, I can have a 1 inside of this row. So here, if I have an edge from vertex 0 to vertex 2, I can put a 1 at row 0, column 2 to indicate that I have an edge from vertex 0 to vertex 2. If I have an edge from vertex 2 to vertex 3, over here I can go to row 2, column 3, and I put a 1 to indicate that we have an edge from vertex 2 to vertex 3. Of course, here I'm assuming that these edges are unweighted, and that's why I either have a 1 if there is an edge, or I have a 0 if there is no edge. But there are also weighted graphs, and if I have a weighted graph, then instead of putting 1s here, I could put the actual weight of that edge, and then a 0 would indicate that there is no edge. So this is how graphs are represented. Any questions about this?
Professor, isn't this format not space efficient because it needs n squared and usually the graph is sparse, not dense?
Right, exactly. So somebody correctly observed that this adjacency matrix format is not a very efficient representation of the graph because it's sparse, and we've already looked at sparse matrices, and that's by design. We cover sparse matrices before we cover graph traversal. Because how do you think we can represent this graph in an efficient manner?
List of lists.
We can have a list of lists. That's going to be very pointer intensive, not going to result in very friendly memory accesses on the GPU. But we've already seen how to represent.
It's a sparse matrix.
Right. It's a sparse matrix, so we can represent it using these sparse matrix formats that we've already seen. So the adjacency matrix is usually very sparse, right? And that's why we can use the same storage formats that we've seen that we can use for sparse matrices. In this class, we're going to assume that all the edges are unweighted, right? So we don't need to, we just need to store kind of the column indices to indicate where there are non-zeros, but we don't need to store the values of these non-zeros. Okay, is this clear? Any questions? Okay, so let's see how we can represent these this graph using the sparse matrix formats that we looked at. In particular, I'm going to look at COO, CSR, and CSC. You can also represent graphs using some of the other formats that we looked at. That's, I think, an orthogonal topic. So we've already looked at different formats and their trade-offs. In this lecture and next lecture, we're only going to focus on COO, CSR, and CSC. All right? So how do I represent this graph using COO? Well, to represent the graph using COO, I need to store the coordinates, which are in this case the source and the destination vertices of each edge. So basically, instead of having a list of non-zeros in sparse matrices, we had a list of non-zeros with the row index and column index. Here, we're going to have a list of edges with their source vertex ID and their destination vertex ID. So a COO representation of this graph, actually, let's start with CSR. Actually, I'll show three, but let me explain COO first. So a COO representation of this graph would look like this. Here I have an edge going from vertex 0 to vertex 2, so I'm going to have 0 as a source vertex and 2 as a destination vertex, and this represents an edge. I have an edge going from vertex 1 to vertex 0, so here in the COO matrix I will have a 1 here as a source and then 0 as the destination to indicate that I have an edge going from vertex 1 to vertex 0, etc. So this is what a COO representation of the graph looks like. It's basically a list of edges. What about a CSR representation? For the CSR representation, what we're going to do is we're going to have a CSR representation of this graph, which means that we're going to group the edges that are going out of the same vertex together, and then we're going to, so here I'm going to have this edge will come here, and I'm going to indicate the destination of that edge, and then here in the source pointers I'm going to indicate where the edges of each the outgoing edges of each vertex start. So here what this says, the source pointer says that the outgoing edges of vertex 0 start at 0, right? And the destination is 2. So this indicates that I have an edge from vertex 0 to vertex 2. Then over here it says that the outgoing edges of vertex 1 start at index 1 in this array, and it ends at index 3, which means we have 2 outgoing edges from 1. And then the destinations of these 2 outgoing edges are 0 and 2, because here the vertex 1 has outgoing edges to 0 and to 2. So here the CSR representation is basically indicating the outgoing edges of each of the source vertices. And the source pointers array tells us where the destination indices of the outgoing edges of each of these vertices starts. And of course, wherever the next vertex's outgoing edges starts, the previous one ends. Here it's a coincidence that the size of the source pointers is the same as the size of the destination, but that's just a coincidence. Usually these two arrays are not the same size. Usually the number of edges is much larger than the number of vertices, so the destination array is going to be much larger than the source pointers array. Is this clear? Is the CSR representation of the graph clear? Yeah? Okay. So then we also have a CSC representation, and the CSC representation is going to store for every vertex as a destination vertex, right? It's going to store the edges in that column. In other words, the edges coming from all the different vertices as sources, right? So here for this column, we will have this non-zero. For this column, we have this non-zero. For this column, we have this edge. These edges, for this column, we have this edge. So here, the CSC representation is putting together the incoming edges of each vertex. For vertex 0, we have an edge coming in from vertex 1. Here, we look at vertex 0, we have an edge coming in from vertex 1. Here, for vertex 2, we have 2 edges coming in, one from vertex 0 and one from vertex 1. So here, for vertex 2, we have 2 edges coming in, one from vertex 0 and one from vertex 1. So when we look at the column of the columns of these adjacency matrix of this adjacency matrix, they represent the incoming edges of each vertex. So when we have the CSC representation, what we have is for every vertex as a destination vertex, we have the sources of the incoming edges for that vertex. So here, this 0 indicates that the incoming edges of vertex 0 start at index 0 and end at index 1, and here the source index of that incoming edge is 1, right? In other words, the vertex 0 has an incoming edge from vertex 1. If we want to find the incoming edges of vertex 2, we come here. It tells us that at index 2, the incoming edges to vertex 2 start at index 2 and end at index 4. So here we go to index 2, and we know that the 2 incoming edges to vertex 2 are coming from the source vertex 0 and the source vertex 1, which, as we can see here, the incoming edges to vertex 2 come from source vertex 0 and source vertex 1. Okay, is this all clear? Any questions? So in other words, you can think of the COO representation as a list of edges. You can think of the CSR representation as a list of outgoing edges for each vertex. And you can think of the CSC representation as the list of incoming edges for each vertex. Any questions? Okay. So if there are no questions, let's talk about how we would parallelize a graph algorithm in light of these different representations. So if we want to parallelize a graph traversal algorithm, there are generally different ways of doing that. We have a vertex-centric approach, and the vertex-centric approach is where we assign a thread to every vertex to do something for that vertex. Okay, we have a thread for every vertex to do something for that vertex. Then we have and for these, we typically use CSR and CSC, right? Because if I want to do something for the vertex, that means I probably want to iterate over the outgoing edges or the incoming edges of the vertex. So we would need a representation that allows us to access that, which are the CSR and the CSC representation. Right? Given a vertex, it's easy to find all the incoming or the outgoing edges. We might also use other representations like the ELL and the JDS representations and optimizations. But like I said, that's not going to be the focus of today. The focus of today is going to be more about the different ways of parallelizing graph algorithms. Okay, the other approach is the edge-centric approach. So the edge-centric approach to parallelizing a graph traversal algorithm is to assign a thread to do something for every edge, right? So every thread takes an edge and the thread does something for that edge. Now, obviously, if a thread is going to do something for an edge, it probably wants to look up the source vertex of the edge, the destination vertex of the edge, etc. And usually, the convenient representation to use for this kind of parallelization is the COO representation. Why? Because in the COO representation, given an edge index, it's easy to go and find what are the source and destination vertices for that edge. Is this clear? Any questions? Is the distinction between doing a vertex-centric and an edge-centric parallelization clear? Okay. We can also have a hybrid representation. And in a hybrid representation, there are certain situations where we might want, for example, to, given an edge, look up the endpoints of that edge, so the source and the destination of the edge, but then we might want to also go through the adjacency lists of each of those endpoints, okay? So we might need to find the neighbors of the source vertices and the neighbors of the destination vertices of an edge. So in this case, we would need the COO representation in order to, given an edge, find its endpoints. But then we would need the CSR or the CSC representation so that given the endpoints, find their neighbors. So it's common for us to use hybrid representations where we have both a COO representation of the matrix of the adjacency list and the CSR or CSC representation of the adjacency list. And by the way, this also applies to adjacency matrices, so to sparse matrices. So we didn't see this with SPMV because we didn't need it, but in other sparse matrix computations, we might need to, given a non-zero, find the row and the column, but then for each of the rows and the columns, traverse the non-zeros in those rows or in those columns. And that's why in your project where you're asked to do a sparse matrix triangular solver, we gave you all the options. We gave you a CSR, a CSC, and a COO representation so that you can reason about whether you need one of these representations, whether you need two of them, or whether you need three of them. Okay. Now for BFS and for SPMV last time, we're only going to need one. We don't need multiple. But I'm just making you aware that there are some algorithms where we might need multiple of these representations. So we would store multiple of them in order to use. Okay. Is this clear? Any questions? Okay, so the example graph algorithm that we're going to use, we're going to cover today is breadth first search, right? We're going to use this as an example graph traversal, but a lot of the concepts that we will talk about are also applicable to other graph traversal algorithms. But I'll look at, we're going to be looking at breadth first search, and we're going to be looking at a particular formulation of breadth first search where we start from one source vertex and we want to label, so we're not necessarily doing a search, but we want to label every other vertex in the graph based on how far away it is from that source vertex. Okay, so here we're gonna, the objective is to find the distance. We're also gonna call the distance the level of each vertex from some source vertex. So here, if I pick a random source vertex in my graph, this vertex is going to be level 0. By the way, I could have multiple source vertices, but in this today we're only going to look at the case where we have one source vertex. But we could have multiple vertices in level 0. But here I have one vertex, and then what I want to do is I want to find all the vertices that are 1 away from this vertex and label those as being in level 1. And then I want to label all the vertices that are 2 edges away, so the neighbors of these level 1 vertices that are not already visited, I want to label those as being in level 2, because for these vertices, I need 2 hops to be able to reach them from the source vertex. And then for all the vertices that haven't been visited that are neighbors of the level 2 vertices, I'm going to label those as being in level 3, because for any of these vertices, I need 1, 2, 3 hops to be able to get to those vertices. And then any of the vertices that are not reachable, I'm going to label those as infinity. Initially, I'm labeling everything as infinity, right? But as I iterate through my graph, I label all the vertices as having a particular, being at a current level. And then any vertices that I don't reach, I will end up labeling as being at infinity, will remain labeled as being at infinity. Is this clear? Any questions about the formulation of BFS that we're covering?
Doctor, how do we know that we're gonna start from a node that exists in the largest graph possible? What if we started in one of the red nodes, for example?
We could, right? That's a different formulation of the problem, right? Here, I'm interested in finding how far all the vertices in the graph are far away from this specific vertex, correct? I might be interested in finding how far all the vertices in the graph are far away from another vertex, like this one, right? In this case, this will be vertex 0, this will be vertex 1, and everything else will be infinity.
Okay, thank you.
Clear? Yeah, you're welcome.
Professor, can I
Yes.
ask you about something that back in the hybrid approach, because I wasn't able to open the microphone. So can I ask you to re-explain why do we use a hybrid approach? Because I didn't get that idea.
In some computations, you might want to do multiple types of traverse accesses. You might want, for example, given an edge, look up its source and destination vertex, and then you might want to iterate over the adjacency list of the incoming edges or the outgoing edges of those source and destination vertex, right? So that's why you would need a hybrid approach, because each format gives you a particular accessibility. CSR lets you iterate over outgoing edges, CSC lets you iterate over incoming edges, and CO lets you iterate, lets you find the source and destination of a specific edge.
Okay.
Yeah.
Thank you.
You're welcome. Okay, great. So now we've seen how what we want to do for BFS. The question is, how can we parallelize this? Any ideas?
We can start from the source vertex and then we assign threads حسب how many neighbors it has, and then maybe call another kernel function that would label this as 1, and then it ترجع على original function, and then it searches for its neighbors, and then it calls threads حسب قد إيه فيها. But it's complicated, I don't know.
Okay, so basically for every level, you're saying we're going to assign a thread to label threads to label the neighbors of that vertex, right? And then next level, we'll assign threads to label neighbors of those vertices, etc., etc. That's the kind of general idea of what you said. Now you said there's some complexity in figuring out how many threads we need to launch, and in order for us not to launch too many threads. And this is something that we will talk about later on, maybe in the next lecture. But in today's lecture, we're going to follow the approach of launching.
Can we assign a thread for each vertex, and if it has an edge whose source is the main node, we set its level to 1. If not, we wait until the other threads are done. If
Right,
all other threads are done, we know it's infinity.
Right. So what we can do is we can assign a thread to every vertex, and that thread can check if the vertex should be, if based on whether that vertex has been visited or not, we can check whether that thread whether that thread should go and start iterating over the neighbors of that vertex. Okay. Now it's complicated to kind of in the same kernel wait for the other vertices to be visited. So what we will do is we're going to launch a kernel for every level, and in every level, that kernel is going to be responsible for labeling vertices in that level, right? And to label vertices in that level, every thread will be assigned maybe to a vertex, and the thread will check if that vertex should be visited or not. Okay, so remember we talked about vertex-centric versus edge-centric. So what we described right now is a vertex-centric approach, and there's actually two versions of the vertex-centric approach, which we will talk about. So the first version of the vertex-centric approach is the push approach. And the push approach is where we assign a thread to every vertex, and that thread is going to push the information from that vertex to all the outgoing edges, right? As opposed to a pull approach where we assign a thread to every vertex and that thread pulls the information along all the incoming edges, okay? So a vertex-centric push approach is where every thread takes a vertex and that thread iterates over the outgoing edges to push information. In this case, the information is the level, okay? And what we want to do is we want to find if a vertex is in the previous level, we want to mark all its unvisited neighbors as being part of the next level or the current level, okay? So here the vertex, every vertex is going to push the information to its outgoing neighbors. So if you think of if we look at an example, let's focus on the kernel that's going to start from level 1 and go and visit all the level 2 vertices. So here we assume all the level 1 vertices have already been marked as being in level 1, and I launch a kernel in order for me to mark all the vertices that should be in level 2. So in this case, what I will do is I will assign a thread to every vertex. Now, all the threads that are not, whose vertices are not in level 1 are not going to do anything, right? They don't have anything to do. But for the threads whose vertices are in level 1, these threads want to push that information to their neighbors by marking their unvisited neighbors as being part of level 2. Is this clear? Yeah? So this is how we're going to parallelize this BFS iteration using the vertex-centric push approach. Every thread takes a vertex, and then the relevant threads will push the information along their outgoing edges. So here, this thread is going to mark this vertex as being in level 2. This thread is going to mark this vertex as being in level 2. And notice that in this case, we could have multiple threads. So this one and this one over here, both marking the same neighbor as being part of level 2. But that's okay, right? Because if both of them mark it as being in level 2, or one of them mark it as being in level 2, the result is the same. That neighbor is going to be marked as being part of level 2. Is this clear?
Professor,
any questions? Yes.
the threads that are not so we launch a thread for every vertex, and there's a lot of threads that are inactive at a time because we are only targeting one level.
Yes, that's right. This is the approach we're going to use now. Now we're going to talk about whether this is efficient or not, or when it's efficient, and whether we can do something better later, right? But for now, this is the approach that we're doing. And I know you're observing there's an inefficiency here, and we'll talk about the trade-offs between the inefficiency versus the overhead of having to manage launching threads only for the active vertices. But yes, right now we're launching a thread for every vertex. Each thread is going to check is my vertex relevant or not, and then only the threads assigned to relevant vertices that are in the previous level will go and iterate over their names. Clear? Okay, so this is clear. Let's go and implement this. I'm going to switch here to the code. So here I've already kind of set up some code for us to do the implementation. So we have our CSR graph. Why do we need CSR? Because over here, every thread is going to iterate over the outgoing edges of its vertex. So the representation that allows us to iterate over outgoing edges is the CSR graph representation. So here, if I look in the representation of the CSR graph, you'll notice that we have the number of vertices, the number of edges, and then we have the source pointers, which tells us where the edges of each source vertex start, and then we have destination indices, which tells us the destination index of each of those edges. Okay, So, and then if you look down at where we're launching the kernel, over here, the number of blocks is decided based on the number of vertices. So we're going to launch a thread for every vertex. And then here we're going to keep iterating. And for every iteration, we have this flag, new vertex visited, that we initialize to 0. And then we pass that flag to the kernel. And then we copy it back. And then we check if that flag has been set. So if the kernel visits a new vertex, it's going to set this flag, and we're going to decide whether or not to keep iterating based on this flag. So if I launch a kernel and this flag is not set, that means I am done visiting all the vertices and the search is over. Is this clear? Okay, so now let's go and implement the kernel. So remember, this kernel is going to have a thread assigned to every vertex. And if that vertex is in the previous level, the thread is going to mark its unvisited neighbors as being part of the current level. So the first thing I need to do is I need to assign a thread to each vertex. So here I can do that by writing vertex is equal to blockindex.x times blockdim.x plus threadindex.x, and then I do a boundary check. So if the vertex is less than the CSR graph dot the number of vertices. Okay, so now every thread is assigned to a vertex, and we have done our boundary check. Okay, so now what do we need to do? So every thread needs to check whether its vertex is in the previous level or not, in order for it to decide whether to iterate over the neighbors or not. So how do we check that? So over here, among my parameters, other than the CSR graph, I have this level array. The level array is going to be tracking the level of each vertex, right? Initially, the source vertex is going to have level 0, and everything else is going to have level infinity. Okay, and then this is the flag that we're going to set if we visit a new vertex, and here current level tells us what current level we are generating. So in the first iteration, this is going to be level 1. Okay, so what we want to do now is we want to check if the vertex that the thread is assigned to is part of the previous level, which is current level -1. So to do that, what I'm going to do is I'm going to write if the level of my vertex is equal to the current level -1. Is that clear? So if the level of the vertex is equal to the current level -1, that means that this vertex should be active, and the thread that should be active, and I need to go and iterate over the neighbors. Now, how do I iterate over the neighbors? Well, I have the CSR pointer in the CSR graph representation, I have the source pointers that tell me where the edges of this vertex start. So I can use that to iterate like we did with sparse matrices. So I can write for unsigned int edge is equal to CSR graph dot source pointers of vertex. So this tells me where is the first edge of this vertex, and then edge is less than CSR graph dot source pointers of what?
Vertex +1.
Right, vertex +1, because the edges of this vertex are going to end where the edges of the next vertex start. And then I do plus edge. So by doing this now, I'm iterating over the edges of this vertex. What do I want to know about these edges? So every thread here is going to iterate over its outgoing edges. What do I want to know about these edges?
Their level.
I want to know the destination of the edge, right? I want to know the neighbors. I'm iterating over the edges to find the neighbors, and then you're right, I'm going to have to look at the level of those neighbors. So for every vertex, I want to get the destination of that. So for every edge, I want to get the destination of that edge, so I can get that from the CSR graph. So I'm going to write unsigned int neighbor is equal to CSR graph dot the destination of the edge. Okay, great. So now I have I'm iterating over the neighbors. What do I want to do with these neighbors?
If their level is infinity, we want to update it. If
Right.
it's not, then we don't do anything.
Right, exactly. So here, this vertex, for example, it has two neighbors. It has this one over here, and it has this one over here. This neighbor here on the right is already marked as level 1, so I don't want to touch it. But this neighbor, because it's not visited before, its level was infinity, I want to mark it as being part of the current level, which is level 2. So here, what I want to check is, I want to check if the level of the neighbor is infinity. So if the level of the neighbor is infinity, so here to represent infinity, I use the largest integer, which is uint max. Okay, so you can just use uint max to represent the level of the neighbor. So here, if the neighbor level is infinity, meaning the neighbor has not been visited, what do I want to do with this neighbor? I want to mark the level of the neighbor as being the current level. Is this clear? Any questions?
Professor, isn't this a race condition? Even though it's a benign race condition, but you said that this results in undefined behavior, so
Right,
it's
you're
better that
absolutely
way
right.
atomic.
Yes, you're absolutely right. So here, marking this neighbor as being level 2 and having multiple threads mark it as being level 2, this is a race condition. Now, it's an idempotent operation because all the threads are writing the same value. So it's an idempotent operation, so it's a benign race condition. Now, in the C++ semantics, even if you have an idempotent operation, race conditions could result in undefined behavior. But I'm not going to worry about that here. But if you want to be very conservative, what you should do is you should use an atomic operation to mark the level. Okay, and then after marking the level, I also want to inform the host code that a new vertex has been visited so that it continues iterating. So I need to set this flag, the new vertex visited flag. So I'm going to mark new vertex visited. I'm going to set that to 1 to notify the host to keep iterating. And this is also a race condition because I have multiple writes, but it's an idempotent operation. So the race condition is benign. But again, in C++, even if you have an idempotent operation, you should use atomics if you want to be kind of very conservative. Otherwise, it could be undefined behavior. Now, in practice, this is not going to result in undefined behavior. This will execute correctly, but you should be aware of this if you're writing C++. Okay. So now,
Question,
so this is the code for
Professor?
performing a BFS level. Any questions? Yes, go ahead.
Why would it exactly result in undefined behavior?
It's just part of the C++ semantics. If you have a race condition, it results in undefined behavior, which means if the compiler detects a race condition, it can do kind of it can do anything it wants.
Okay.
Professor, can you please show us the loop again because I didn't catch it. the screen wasn't updating on the
Okay, the loop is this one. The loop is right here.
the loop, not this one. The loop that launches the kernel.
Yes. So if I scroll down, so down here you have a loop. The loop, it starts from level 1 because level 0 is already initialized to the source vertex. Okay, and it keeps iterating until the flag, the new vertex visited flag, is no longer set.
Okay.
And for every iteration, it's going to launch a kernel, and then it's going to copy back that flag and check if that flag has been set. Is that clear?
Yes. Okay. Thank you.
You're welcome. Okay, let's compile and run this. I'm going to compile. Okay, I'm going to run. Okay, and as you can see, here our kernel takes around 4.45 milliseconds to execute. All right, so keep that number in mind so that we go look at other implementations and compare this number to the performance of other implementations. Okay, so and this here is the code that we wrote as usual. So remember, we said that there are different ways of parallelizing. We looked at the vertex-centric push approach, which assigns a thread to each vertex and pushes the information along the outgoing edges. What's another way that we can parallelize this computation?
The incoming edges. We look
Right,
at the
so we
incoming
can
edges.
have a vertex-centric approach where a thread assigned to every vertex, but we iterate over the incoming edges. And we call this the pull approach because the vertex pulls information from its incoming neighbors. Okay, so how would we implement a BFS level using the pull approach? Well, basically, we're going to assign a thread to every vertex, and if that vertex is not visited, we will iterate over all the incoming edges and look if any of their incoming neighbors have been visited. If one of their incoming neighbors has been visited, then we can mark that vertex as being part of the current level. Right, so to illustrate that over here, if I'm doing a vertex-centric pull approach, I'm going to assign a thread to every vertex. The threads that are assigned to vertices that have already been visited are not going to do anything. The threads that are assigned to vertices that have not been visited are all going to iterate over their incoming neighbors. And then those threads where one of their incoming neighbors is part of the previous level will mark their vertex as being part of the current level. Is that clear? Any questions? Okay, so let's implement this. What data structure do we need to implement this? What representation of the graph?
SCSC implementation.
SCSC representation, exactly, in order to iterate over the incoming edges. So let's go and let's implement our BFS pull approach. So here the approach is the same. I launch a kernel that has a thread for each edge, and then but instead I have a CSC representation of the graph, and in the CSC representation of the graph, I have destination pointers. So in other words, I put together the edges that all have the same destination vertex, right? So these are all the incoming edges for that destination vertex, and I have an array that has the source vertices of all those edges. Okay, so first I'm going to assign a thread to each vertex. So unsigned int vertex is equal to blockindex.x times blockdim.x plus threadindex.x. I'm going to do a boundary check. So if the vertex is less than the CSC graph dot num vertices. Okay. So now, if for each vertex, what do I need to do? Well, first I need to check, has that vertex been visited or not? Okay. How do I check that? Well, I'm going to look at the vertex's level. So if the level of the vertex, right, is equal to what? So if the vertex has not been visited, its level will be infinity.
uint max.
In this case, right, I'm representing as uint max. Right? So here, I'm only going to process the vertices that have not been visited yet. Okay? What do I want to do with these vertices? So I've reached a vertex that has not been visited. What do I want to do with it?
I scan its incoming edges to see.
Right, I want to iterate over all its incoming edges. So I'm going to write a loop for unsigned int edge is equal to CSC graph dot source pointers. So this is going to tell me the indices of all the edges in the graph for whom this vertex is a source. In other words, it's all the incoming edges for this vertex.
Destination pointers?
No, the source pointers, right? So the pointers for this vertex as the source vertex. Destination pointers is in the CSC graph. Oh, sorry. Yes, you're right. Excuse me. Thank you for the correction. Yes, all the destination pointers. So I want to look at all the incoming edges. So I want to look at all the edges for which this vertex is a destination. Thank you for that correction. Okay, and then edge is less than CSC graph dot destination pointers of vertex plus 1, and then plus edge. And then for each edge, what do I want to find out? So here, this vertex iterating over the edges. For each edge, what do I want to get? I want to get the source vertex of that edge. So I'm going to write unsigned int neighbor is equal to CSC graph dot source of edge. Okay, great. So now for every for every vertex that's not been visited, I'm iterating over the incoming edges and I'm finding the source vertex of that edge. What do I want to do with that source vertex?
If its level is valid,
Right, I want to
we
check if that
increment
source
our level.
vertex is in the previous level, right? So I will do if the level of the neighbor is equal to the current level minus 1. And if that is the case, what do I want to do? So if I find that this vertex has a neighbor in the previous level, what do I do with it?
We just set our level to be the previous level plus 1.
Right, I label it as being part of the current level. So I do level of the vertex is equal to the current level. Okay, and of course I need to set the flag to indicate that I visited a new vertex. So new vertex visited equals 1. Is that clear?
Professor, wouldn't it be slightly, like ever so slightly more efficient to just check if the level of neighbor isn't uint max?
So somebody's asking, should I check if the level isn't is
Instead
not
of
equal?
checking if it's less, if it's equal to current level minus 1, we can just, isn't it slightly more efficient to check the not equality with uint max?
Yeah, you can do that.
But wouldn't this
But
cause us
if it wasn't uint if it was anything besides the current level minus 1, then that means you would have already visited it. Does somebody have a question?
Yes, I was saying that wouldn't that let us visit vertices that we've already visited if we set it equal to uint rather
Well, we're
than
not going to
checking?
visit versus we haven't visited because we've already checked if the level of the vertex is.
Oh, okay, yeah, okay.
Okay,
No.
great. Anything else that I can do here? Is there anything else I should do, or am I done?
I should break
Right, I can break, correct? I can break. Why can I break?
because I just need to find out if this particular vertex needs to be marked in the current level or not. And if I've already found that I have a vertex in the previous level, then I'm done. I don't need to check more vertices.
That's exactly. So here, this thread over here, as long as it finds that one of its neighbors is in level 1, it can mark its vertexes in level 2 and break. It doesn't have to go and check other neighbors to check if they're in level 1. Okay? And this is actually an advantage of the pull approach in this particular scenario over the push approach. Because in the push approach, if I have a vertex with a very large number of outgoing edges, I have to iterate over all of them at some point. Whereas in the pull approach, if I have a vertex with a very large number of incoming edges, I don't have to iterate over all of them. I only have to iterate until I find a vertex that has not been visited. Is that clear? Okay, so then let's compile and run this code and see if it works. So I'm going to compile and I'm going to run. And you'll notice that our execution time now has gone down to 1 millisecond as opposed to 4.45 milliseconds, right? Where do you think this benefit is coming from?
The break.
The break, exactly. It's coming from the fact that we have much better load balance than in the push approach, okay? So the pull approach has the advantage over the push approach in that if I have very long neighbor lists, the pull approach the push approach is going to iterate over them, whereas the pull approach is going to break early. Does the push approach have benefits over the pull approach?
Yes, because in the pull, if we're at the beginning, we will have to scan all of the vertices that multiple times before we start getting levels propagating across the vertices. But with push, we only have to do it for the vertices that we're starting with.
Right, exactly. In the push approach, I'm only going to iterate over the neighbors of a vertex once in the level where when I am visiting the level where that vertex is in the previous level. Whereas in the pull approach, I'm going to iterate over the neighbors of each vertex every time until that vertex is reached, right? So if I look at this vertex over here, I'm going to iterate over the neighbors of the first vertex when I go from level 0 to level 1, and then from level 1 to level 2, and then from level 2 to level 3. Okay, so the push approach has the benefit of only iterating over the neighbors once. So in the early levels, in the very early levels where I haven't visited many vertices yet, the push approach is advantageous because it's only going to iterate over a few neighbors, whereas the pull approach is going to iterate over everybody's neighbors because most vertices haven't been visited yet. In later levels, when most vertices have been visited, the pull approach is much better because it's going to break early out of iterating over the neighbors of vertices with very high degree. Is that clear?
Is there a way to make a hybrid approach?
Exactly. So having observed that, so here, this is the code that we wrote, and having observed that, we can actually have a hybrid approach, and this is called a direction optimized approach, where we can start with the push approach and then switch later to the pull approach. Because pull is inefficient in the beginning because most vertices haven't been visited, so we have to search all their neighbors. So we can start with push and then then switch to pull later on. So actually, I already have an implementation that does that. We're not going to implement it for the sake of time. So here, I have already implemented a version, a kernel that has both the pull and the push approach. And over here, we're going to call the pull or the push depending on the level. In particular, for the first level, we're going to do push, and then later we're going to do pull. By the way, another name for push is top down, because if you think of the BFS tree, you're pushing from the top, the parent, down to the children, versus another name for pull is bottom up, because you're pulling from the you're pulling from the parent down to the child. Okay, so let's run this and see how this hybrid version where we do push in the first iteration, then switch to pull does. Right, and as you can see, we're down to 0.459 milliseconds, which is faster than doing just push or just pull. Is that clear? Any questions about this? Okay, great. So now we've seen that we have vertex centric. We can do push, we can do pull, or we can do hybrid, a direction optimized approach. What was the other way to parallelize graph traversal? So besides vertex centric, what can we do?
COO, edge centric.
Edge centric, exactly. So the other approach was edge centric, where we assign a thread to every edge. And in the context of BFS, what that would do is every thread is going to look at an edge. It's going to check if the source of that edge has been is in the previous level, and the destination has not been visited. I mark the destination as being in the current level. Is that clear? So to illustrate that, so here, what I will do is I will assign a thread to every edge. Then every thread whose previous vertex is in the whose source vertex is in the previous level and whose destination vertex has not been visited, that thread is going to mark its destination vertex as being in the current level. Okay, so here these threads whose destination is in level 1 and whose source is in level 2, these will be active, and all the other threads will be inactive. Is this clear? Any questions? Okay, let's implement this. So I'm going to go, and now let's go and implement the edge-centric approach. So for the edge-centric approach, how many threads do I need? I mean, a thread for every edge, right? So here the number of blocks is going to be set based on the number of edges as opposed to the number of vertices in the graph. And also I need what kind of graph? I need a COO graph, right? Because the way this works is for every edge, I want to look up the source and the destination vertices of that edge. And that's what COO gives me. So here, if I look at the representation of the COO graph, I have the number of vertices, number of edges, and then I have the source and the destination of each edge. Is that clear? Okay, so I'll assign a thread to every edge. So I'm going to write unsigned int edge is equal to blockindex.x times blockdim.x plus threadindex.x. Here, every thread is taking an edge. I do a boundary check. So I'm going to check if the edge is less than the COO graph dot the number of edges. Okay, and what do I do in this case? So for
Check
every
if the
thread
source.
is going to check, yes?
Check if the source is a level of the source is cur level -1.
Right, exactly. So I'm going to check if the source is in the current level -1. So let me get that source vertex. I'm going to write unsigned int vertex is equal to COO graph dot source of the edge. I'm going to get the source vertex of the edge. I'm going to check, is the source vertex in the previous level? So if the level of the vertex is equal to the current level -1. Okay, and then now what I do? What do I do? So if
Update
the source is in the
destination.
next, what do I need to do? I need to check if
The destination is visited.
the destination is visited or not. So I'm going to do, and to get the destination vertex, I'm going to write unsigned int neighbor is equal to COO graph dot destination of the edge. I'm going to get the destination of the edge. And now I'm going to check if that neighbor is visited. So if the level of the neighbor is equal to uint max, that means the neighbor is not visited. Okay, and in this case, if my source is in the current level, in the previous level, and my neighbor is not visited, what do I want to do? I want to mark the vertex as being in the current level, or the neighbor. So I will do level of neighbor is equal to the current level. And of course, I can set the flag to indicate that I have visited a new vertex so that we keep iterating. Is this clear? Anything else we need to do? All right. So so now we've seen how to implement the edge-centric parallelization for a breadth-first search iteration. What do you think are the advantages of this edge-centric approach over the vertex-centric approach?
If we have more edges than vertices, then it's probably better to use a vertex-centered approach and vice versa.
If we have more edges than vertices, it's better to use what? A vertex-centric or an edge-centric? So usually we have more edges than vertices, right? And normally in graphs, we have many more edges than vertices. So the edge-centric approach, its advantage is that it extracts more parallelism, correct?
Yes.
Yeah, it extracts more parallelism. What's another advantage of this edge-centric approach compared to the vertex-centric?
We don't have to loop inside the kernel.
Right, we don't have to loop. And what does it mean if we don't have to loop? What do we get rid of?
Control divergence.
Right, the control divergence. Because we saw that with the push approach and to less extent with the pull approach, the loop meant that adjacent threads were looping for a different number of iterations based on how many neighbors they have, right? So we had control divergence. In the edge-centric approach, every thread had one edge that it processed. So every thread did the same exact amount of work. We didn't have any notable control divergence. Is this clear? I mean, obviously we have some control divergence because some threads will visit that edge and some threads will traverse the edge and some threads won't. Okay, but it's either you do one traversal or no traversals, as opposed to in the vertex-centric approach where adjacent threads might do a very different number of edge traversals. Right? So let's compile and run and see how this performs. I'm going to compile. And I'm going to run. Okay, and as you can see, the edge-centric traversal performs better than the vertex-centric approach or the push approach or the pull approach on their own. Its performance is similar to the direction-optimized approach because because that approach kind of gives us the best of both worlds for the pull and the push approach. But if you compare it to just the pull or just the push, the edge-centric approach is better because it reduces control divergence. Is this clear? Any questions? Right, and this here is the code that we just wrote. Okay, so is the edge-centric approach always better than the vertex-centric approach? So here the answer is no. It really depends on our data set. So the best parallelization approach usually depends on the structure of the graph that we have. So the vertex-centric pull approach and the edge-centric approaches are better at dealing with load imbalance, and that makes them better on graphs that have very high degree, right? So these are graphs like social network graphs and graphs with a lot of celebrities. So if I like social network graphs, if they have a lot of celebrities, right? So usually if you have celebrities, mean like if you have a few vertices that have a very large number of neighbors, this is really bad for the push approach, and that's where the edge-centric pull approach, sorry, the edge-centric approach and the vertex-centric pull approach shine. But what if I test on a graph that doesn't have a very high degree? What kind of graphs don't have high degree? A road graph, right? Like if I test on something like a road graph is a graph that captures the map of a road, right? A road network inside of a map, right? So the road graph is not going to have a lot of a very high degree, right? Because usually every vertex will represent an intersection and every edge will represent a road connecting two different intersections. So in a road graph, right, every intersection is going to have a maximum of, 4, 5, 6, maybe even 8 in a very complicated intersection. But there's going to be a limited number of roads that are coming in and out of that intersection. Okay, so let's go and test each one of these on a road graph and see how they perform. So I'm going to go back to the BFS-centric push approach that we developed. And by default, I've been using a social network graph, which has a high degree and a lot of celebrities. But let me go and change the default data set and instead use a road graph. So here I'm going to test on a graph that represents the road network of the state of California. So here, if I run on this road graph, okay, it seems that okay, there we go. So here I get so this road graph is larger than my social network graph, so I get 25 milliseconds for the push approach. Let me go check the pull approach. So notice that it actually runs. Oh, sorry, that was the push approach. Excuse me. All right, so here you can see that the pull approach actually runs significantly slower than the push approach, right? As opposed to when we had the graphs that had high average degree, the push approach was actually for the edge-centric approach, it actually is slower for this low degree graph. Okay, so here it's clear that the best graph really depends on the best parallelization approach depends on the structure of the graph. The vertex-centric pull and the edge-centric approaches were better on the high degree graphs because they were better at dealing with load imbalance, whereas the vertex-centric push approach was better on the low degree graphs. And the reason is that for the high degree graphs, because you have high degree vertices, the levels grow very quickly and you have a small number of levels. Whereas for the graphs that have low average degree or low maximum degree, the levels grow very gradually. Every level has a small number of vertices and there are usually many, many levels. And that's why with the push approach, we're in each level we're only looking at the promising threads and we're avoiding iterating over all the neighbors of all the other threads. Whereas for the pull approach and the edge-centric approach, they don't have the benefit of load imbalance. However, what they're gonna do is they're gonna be visiting, but iterating over the neighbors of most of the edges on every iterations. And because we have a very large number of iterations, that cost is gonna catch up to us. Okay, so as you can see, the best parallelization approach depends on the data set in question. Any questions about this concept? All clear? Okay, so one final point is you may have noticed that there was a similarity between our BFS implementations and our SPMV implementations. If we go back to SPMV, right, we were multiplying a sparse matrix by an input vector, get an output vector. And what we did is we iterated over every row, maybe in parallel, and then we iterated over every non-zero in that row. And for each non-zero, we looked up the input, we looked up something in the input vector at the corresponding column, and then we updated something in the output vector at the corresponding row, right? This is particularly the CSR implementation. Now, if we look at BFS, and in particular one level of BFS, and if we look at the transposed adjacency matrix, let's assume our destination is here and our source is here. Then what we did is we iterate, here, this is the vertex-centric pull approach. We iterated over every destination vertex. For every destination vertex, we iterated over the incoming edges. And then for each incoming edge, we looked up something in the levels, in the old levels, and then we at the source, and then we updated something in the destination levels at the destination. So in the new levels at the destination. So as you can see, what we do for SPMV is very similar to what we do for BFS. And also, if you look at the others, so the vertex-centric push implementation corresponds to SPMV CSC, and the edge-centric implementation corresponds to SPMV COO. Okay, so with a few minor tweaks, we can actually formulate BFS in terms of SPMV. And it is the case also that many other graph traversal algorithms can be formulated in terms of sparse linear algebra computations. Now, what's the advantage of formulating a graph problem in terms of sparse linear algebra computations? The advantage is that sparse linear algebra have a lot of very well optimized libraries for performing sparse linear algebra. So if I have a graph computation that can be formulated in terms of a sparse linear algebra computation, what I can do is, rather than implementing the graph computation on the GPU, I can simply use an existing well-optimized linear algebra library to implement the graph computation. Now, the disadvantage is that using the linear algebra, we call this the linear algebraic formulation. The linear algebraic formulation is not always the most efficient way of implementing a graph problem, a graph algorithm. Sometimes we can use the fact, our domain-specific knowledge of the graph algorithm to be able to apply certain optimizations that a generic sparse linear algebra library would not apply, right? However, in many cases, right, if you use the sparse linear algebra computation, this can be a quick way to get a high-performance implementation of the graph algorithm without having to do too much work implementing and optimizing. Is that clear? Any questions?
Professor, can you explain why did we transpose the adjacency matrix when we were observing the similarity?
So here I just consider the transpose to make these two implementations work. When we do the BFS formulation, when we do the sparse linear algebra formulation, it's actually a vector matrix multiplication, which is the equivalent of a matrix vector multiplication with the transpose.
Oh, okay.
Okay. So here, because in SPM VCSR, we do for every row, and then for every non-zero in the row, then we do a lookup at the column, and then we do a write at the row. So here, this corresponds to the vertex-centric pull, right, where we look up something in the input levels at the source, and then we update something in the new levels at the destination.
Okay. Thank
Okay.
you.
Any other questions? Okay, if not, then that's all for today. Next time, now some of you observed today that every time we launch a thread, every iteration we're launching a thread for every possible vertex or every possible edge. And a lot of times these threads are just going to check their vertex or check their edge and end up doing nothing, right? So next time we're going to look at an alternative way of implementing graph algorithms that addresses that specific problem. So we'll continue talking about graph algorithms. Next time will be part 2 of this chapter. Okay? All right, thanks everyone. Bye-bye.
Thank you.
Thank you, Doctor. Bye.
Thank you.